చేస్తాను సార్. Good morning to the participants. Welcome to the today's section. Good morning to all the participants. Welcome to this third day section. Today we have the speaker with us, Dr. Vidyasagar sir from United Kingdom. Before starting the section, I want to introduce Dr. Vidyasagar sir to the participants. Dr. Vidyasagar sir is with School of Computing and Engineering, University of Huddersfield, United Kingdom. Star has a strong technical background, and Sir has started his technical education with a diploma in electrical and electronics engineering, and he obtained Bachelor of Technology in electrical and electronics engineering, and Master of Technology in electrical power systems. Then he completed his doctoral work, Doctor of Philosophy. His thesis title is Data Reconciliation Based Scheme for Sensor Default Detection from Homi Bhabha National Institute, Bhabha Atomic Research Center, Mumbai. Then later he completed his postdoctoral work from the Department of Automation, Shanghai Jiaotong University, China, during the year 2021. Now he is with the School of Computing and Engineering, University of Huddersfield, United Kingdom. We are very fortunate to have a speaker with good technical background, and Sir has good teaching experience also. He worked as assistant professor at different institutions, and Sir has research interests related to condition monitoring, fault detection and diagnosis, electronic and software implementation, multi-scale modeling, vibration monitoring, multivariate data analysis, electric vehicle batteries and energy storage devices, health assessment, internal resistance calculation, data analysis and conditioning and control electronics. Sir has published more than 10 publications in reputed journals. And today, Dr. Vidyasagar sir is going to enlighten us on the topic issues related to EV battery SOH estimation. Welcome, Dr. Vidyasagar sir,
Thanks, Anil.
for today's section.
Yeah, thank you very much for the introduction.
Please on the video, sir.
Yeah. Visible, I think.
Welcome, Dr. Vidyasagar sir. Good morning.
Yeah, thank you very much. Good morning. Morning to everyone.
You can share the screen also, sir.
Yeah. So, is my screen visible?
Not yet, sir.
Yes, sir. The screen is appearing, sir.
Okay, okay.
Screen is visible, sir.
Okay, okay.
Start the
So
section.
please let me know when I can start the session, please. I think I can start the session now. Yeah. Good morning to everyone. As Sir introduced, I'm Dr. Vidyasagar Allapu. I am working as a research fellow in University of Huddersfield in School of Computing and Engineering. So I have been working on EV battery health estimation, internal resistance determination for the sorting and classification of EV battery modules based on their health condition. So I will discuss about the issues related with SOH estimation and our experiences in this project and reuse of retired EV batteries. That means once the batteries have come out of these electrical vehicles, those become retired electrical vehicle batteries, reusing them for the sake of environment and for the sake of economy. Coming to the contents, I will discuss about the introduction and brief history of electrical vehicles, problems with electrical vehicles, types of electrical vehicles, EV batteries, performance criteria, and battery parameters, comparison of commercially available batteries, a brief discussion, battery charging modeling, a brief discussion is given here, battery SOH assessment methods, discussion, experimental outcomes and experiences with EV battery module status classification as a part of our project here in the UAH, reuse of retired EV batteries, and I will discuss about this. Coming to the introduction and brief history. So the popular modes of transport we have are air transport, air travel. This requires ATF, air transport fuel, which is quite expensive. And this air travel takes very little time, as you all know, for the journey. Train, and most of the trains we have are electric in nature. So they take electrical energy from the supply lines and they make the linear motion along the track. And the third mode is the road travel. So this road travel also needs fuel, because in road travel there is no predetermined track. So the supply cannot be given through supply lines overhead. The supply lines cannot be given for this road travel. So for this free range operation, we need to rely on this fuel. Air travel, we need fuel. So the road travel, coming to the road travel, IC engine based vehicles are there. Take fuel. Electrical vehicle is there, which works on battery for free range operation. Hybrid vehicles, the combination of these two, which is the combination of the above two. So hybrid vehicles have the IC engine as well as the EV battery. There are two types in this: series hybrid and parallel hybrid. In series, the mechanical energy given by this IC engine is converted into electrical energy through a generator, and this is given to the motor of the vehicle, then it makes the motion. And in parallel hybrid, both the IC engine and this battery um, have the control over the shaft to control the mechanical motion of this vehicle. So need for electrical vehicles. So we are in the short of fossil fuel resources. The earth is facing the shortage of fossil fuel resources. So sooner or later, we need to completely transform to the electrical vehicles. The need for electrical vehicles is energy saving and the reduction of carbon emissions. That is one thing. Reduction of noise and local pollution. Reduction of dependence on oil, which is a extinguishing source. So many cities have declared them as ultra low emission zones or at least low emission zones. This map shows different cities that have declared them as low emission zones or which implemented a congestion charging policy. Means if any vehicle enters into that region, that should be low in carbon emissions, and there will be a congestion charge that is levied on the vehicles for entering into that region. So such zones are indicated in this map: London, Gothenburg, Stockholm, and all. So somehow successfully implemented, and in some cities this policy is in discussion, and there are some failure cases as well. So this is the need of the hour, means reducing the noise and local pollution and the reduction of carbon emissions and energy saving, reduction of dependence on oil. All these are needs of the hour. So as a part of this, we need to go for electrical vehicles. This is the introduction and brief history of electrical vehicles. So the electrical vehicles came into picture with the invention of electrical motor in 1821. In the year 1821, the first electric locomotive came into operation in 1837, which used non-rechargeable batteries. Then electric trams and trolley cars have come into action in 1880. So end of 19th century, mass production of rechargeable batteries has mass production, means they were produced in quantity. Part of 20th century, EVs were a strong contender, reliable, and they started instantly. Electrical vehicles have become reliable, and started instantly. IC engine, at the same time, IC engine became unreliable, smelly, and needs manual cranking. And steam engine, it needed lighting, and it is of low thermal efficiency. In 1920s, lakhs of EVs such as cars, vans, taxis, delivery vehicles, and buses all came onto the roads. Lakhs of electrical vehicles. So this was the golden era for the electrical vehicles. However, at this point, the oil became cheap and self-starting of IC engines became possible. Ironically, the self-starting of IC engines has become possible through this mass production of rechargeable batteries. So these were originally intended for electrical vehicles, but with the mass production of rechargeable batteries and with the possibility of the self-starting of the IC engine, they were just used here. And once oil became cheap, then IC engines again took control over this market. So from this onwards, the EV vehicle, electrical vehicle technology has was on slow pace, and electrical vehicles are being developed in these last 2-3 decades only. So interesting fact, sir, specific energy of petroleum fuel is 9,000 watt hours per kg, and its efficiency is 20%. Coming to the specific energy of lead acid battery, it is 30 watt hours per kg, quite low compared to this 9,000 figure. But the efficiency of conversion, energy conversion is 90%. So we will see an example here. So the problems with EVs, we will just discuss this through an example. So 9,000 watt hours per kg with an efficiency of 20% gives 18,000 watt hours per kg at the gearbox shaft. In case of an IC engine, this fuel is used in IC engine. This is the case of EV. So 30 watt hours per kg with an efficiency of 90% gives 27 watt hours per kg at the motor shaft. So for a 50 kilometers journey, a 4 kg of fuel is required. So the total energy given by this 4 kg of fuel for this 50 kilometers journey is 7,200 watt hours. For the same energy output, because of the low specific energy, the weight of the lead acid battery is about 270 kgs, which is quite massive. 270 kgs of lead acid battery can do the same job as this 4 kg of fuel. For 100 kilometers journey, for the case of 100 kilometers journey, 8 kgs of fuel is required, just doubling the quantity of the fuel. However, the same energy can be given by this 540 kgs of battery, which is double this 270, but will not double the range. Will not double the range because most of the energy given by this battery is consumed in accelerating and decelerating the own weight of the electrical vehicle. By simply doubling the battery capacity, we cannot achieve double the range or higher range. So this is the problem. Accelerating and decelerating the own weight of the battery due to its low specific energy is the problem, main problem. So because of low specific energy, the weight is higher in case of EVs as they use batteries. The charging time is higher currently. Limited range. With all this, we get a limited range considering the weight of the vehicle into mind. We need to reduce the battery size, so the range obtained is limited. The batteries are costly in the current situation, and the battery has a limited life. After 5 or 6 years, or after doing some specified number of deep cycles, that is from 100% SOC to 0% SOC, or 80% SOC to 20% SOC, that is called a deep cycle. SOC, I mean by state of charge. So for doing this 80% SOC down to 20% SOC, the energy in the battery is consumed in terms of ampere hours, the watt hours. So once this this cycle is that is called a single cycle, 80% coming from 80% SOC to 20% SOC. The operation of this electrical vehicle is called a single cycle. If a specified number of cycles have been done by the vehicle, then it is said that the life of the battery has gone. So after specified number of cycles or a few years, we are required to change the battery, which is a lot of expense again. So range anxiety because of the low range, weight, and charging time. So considering the weight of the vehicle, if we reduce the capacity of the battery, there is always range anxiety for the driver. So, however, so these are the problems. However, the specific energy of the batteries is increasing. The specific energy is in watt hours per kg. So this is the case of lead acid battery, as we have seen. Coming to the lithium ion battery, this watt hours per kg figure is increasing these days. The research is being done to increase the watt hours per kg so that for a specific range of the vehicle, the weight of the battery comes down significantly, and which is of very high requirement nowadays for these electrical vehicles. And charging time, fast charging is being developed for the electrical vehicles. So range is also extended if the specific energy of the battery increases. Cost is also coming down with the mass production of the electrical vehicles. So life is also increased with the technology and research. So with all these increased, this range anxiety is also dealt with. So research is being done to fix all these problems. So types of vehicles, electrical vehicles. So pure battery vehicles, that is the first type. Hybrid electrical vehicles, as we discussed. Series and parallel hybrid electrical vehicles. Fueled electrical vehicles. That means those are the electrical vehicles only, but they use fuel cells. Just like we refuel the vehicle with fossil fuel, we need to refuel the vehicle with some fuel, which is a methanol, for example. So this the suppose consider the case of hydrogen fuel cell. Hydrogen fuel cell. So this hydrogen fuel cell, so a hydrogen tank can be there. This is the case of this particular vehicle. A fuel tank is there, hydrogen. So hydrogen can be filled in the tank, and it can drive the mm, vehicle. However, storing the hydrogen in the vehicle is not very practical. So what is done is that a methanol tank is used in the vehicle which can store methanol, that is fuel just like our fossil fuel. Then that methanol is converted into hydrogen for the sake of this fuel cell vehicle. So this is one way of this fuel electrical vehicle. EV is using supply lines like trains, trams. We see in bigger cities, trams. EV is using flywheels or supercapacitors. Whenever there is a requirement for high specific power, that means the vehicle has to be accelerated like anything. We use flywheels or supercapacitors. Solar power electrical vehicles. These solar panels are attached to the body of the vehicle. EV is using linear motors. That means there is a called there is a train called maglev, means magnetic leviation vehicle. So that uses motors, linear motors for making the linear motion. So all these are different types of electrical vehicles. EV batteries that are in wide use. The EV batteries that are in wide use are lead acid batteries, nickel iron battery, nickel cadmium, nickel metal hydride, sodium sulfur, sodium metal chloride, lithium polymer, lithium ion, which is the celebrated battery these days, aluminum air zinc air batteries. So these are different batteries. These batteries are in wide use these days, and research is being done on these batteries. Battery parameters, cell and battery voltages. What can be the cell and battery voltages? So for a typical Nissan Leaf vehicle, this is the company and this is the model, Nissan Leaf EV. The nominal voltage is 3.65 volts and the maximum voltage is 4.2 volts and the minimum voltage can be discharged to is 2.5 volts, but usually discharge is done till 3.3 volts. So this is considered as 100% SOC and this is considered as 0% state of charge SOC. So in between this nominal voltage is 3.65 volts. To cell and battery voltages, ampere hour capacity, charge capacity means amperes multiplied by time. So what can be the range of this amperes multiplied by time? That is this ampere hour capacity. Energy stored, amperes multiplied by voltage multiplied by time. This is the energy stored, that is another battery parameter. Specific energy, as we have seen, this has a unit of watt hours per kg. Specific power, this is watts per kg. Energy density, watt hours per meter cube. Ampere hour efficiency. So what are the ampere hours given to the battery, and that means the ratio of ampere hours obtained from the battery to the ampere hours given to the battery to make it fully charged as to the state before the discharge has been done. Energy efficiency, how much energy was taken out, and what is the energy given to the battery. So that is the energy efficiency, the ratio of energy output to the energy input is energy efficiency, self-discharge rates. So if a battery is mm, left in the storage for quite some time, then the SOC, if the initial SOC is 100%, 100% SOC, then after many days it will not be at this 100%. It may come down to some 90%, 98% SOC typically. So this 2% loss in the state of charge is due to the self-discharge of the batteries. Geometry, what is the geometrical shape of the batteries? Temperature, heating and cooling needs. Some batteries, such as sodium batteries, need external heating for their operation. Temperature, heating and cooling needs. Life and the number of deep cycles the battery can perform. So all these are different battery parameters. So performance criteria is specific energy, energy density, specific power, typical voltages, ampere hour efficiency, energy efficiency, commercial availability, cost, operating temperatures, self-discharge rates, number of life cycles, recharging rates. That means, so if the battery has 65 ampere hours, so its C rate, C number is 65. So charging it with one C rate means we are charging it at the rate of 65 amperes in an hour. That means 65 amperes have been given in an hour. That is called 1C rate. So recharging rates, discharging rates, energy availability of these batteries depend on the ambient temperature. So if the battery is of 65 ampere hours, in case of ambient temperature conditions ranging from 20 degrees to 30 degrees, the capacity will not stay consistent at 65 ampere hours. If the temperature reduces, degrees reduces, then the ampere hours or the capacity of the battery also reduces. Because of this, in cold weather conditions, the vehicles cannot make a good range. Means the range made by the vehicles is limited in low temperatures. So ambient temperature decides this energy availability, charge and discharge rates, battery geometry, optimum temperature, charging methods, cooling needs, all these factors influence this energy availability. So comparison of commercially available batteries, we have lead acid batteries with a specific energy 30 watt hours per kg, as I discussed. Nickel cadmium, nickel metal hydride, Zebra, zero emission battery research association battery, lithium ion battery 150. This lithium ion battery is has become famous because of this high specific energy number. With this high specific energy number, we can just compare this specific energy number with that of lead acid battery. It is 5 times higher. Means for the same range to be made by the electrical vehicle, the weight of the lithium ion battery is 5 times lower compared to that required when a lead acid battery is used. The weight drastically or significantly reduces if the batteries of high specific energy are used, such as lithium ion. So that is why this lithium ion battery has become famous. So energy density numbers we can see 75, 80, 150, 150, 150 here. Specific power 250 watts per kg, 150, 200, 150, 300 here, which is relatively quite better. Coming to the cost, it is that means comparison has been made by taking the cost of the lead acid battery as reference. It is 1 here. So it is 3 times higher than the lead acid battery for the same range. It is 4 times higher compared to this one. 4 times higher here again. Coming to the cost, lithium ion battery is 6 times higher than that of the lead acid battery for the same range. So research is being done to increase this much further and to reduce this further down. So research is being done in this direction. And one more thing to discuss is the battery charging. So every particular battery is of a specified chemistry. So for that, it has to be charged in a particular manner with some particular charging rate or discharging rate. It has that means a proper battery charger supplied by the manufacturer or the original battery charger that has come with the equipment has to be used. So if fast charging is used for normal batteries, it seems that that is working fine and the battery charges fast, but its performance deteriorates over time. So that is why the chargers intended for that particular battery are to be used. Or if artificial, that means some the charger is made explicitly made, then this charging rate is to be considered into the mind. Charge equalization, this is one more important criteria to be discussed. If there are number of cells connected in series in a particular battery, we need to consider this self discharge of the battery in mind. Self uh, discharge, self discharge of the batteries in mind. I have considered two different cells of different self discharge rates. Cell A with very less discharge rate, self discharge rate. Cell B, which is relatively of higher self discharge rate. So in this case, in the case of charge equalization has not been done. Charge equalization has not been done in this case. So I'm describing the case here. So the cell A is fully charged and cell B is fully charged, and much time is not given immediately. 50% discharge is made. Then 100 has to become 50 here because of the discharge. 100 has to become 50 here. These are connected in series. Then because of the low self discharge, this 50 percent has become 48%, and because of higher self discharge, this 50 has become 40% here. Then 50% recharge, then 98, 90. This has become 40, has become 90 here. Then 60% discharge. This has to become ideally 38%, but because of the self discharge, 35%, and it has to become 60% discharge means 30% because of the higher self discharge become 19%. So no, this recharge and discharge are being done here this way, but there is always some difference in the self discharge. So this difference is increasing here. So with 50% recharge, this is at 59 only, while the other is 83. If the same battery is discharged by 60%, then the percentage of SOC of the battery A is 18%. Coming to battery B, it has become lesser than 0%. And after that, there is self discharge also, so it has become less than 0%. SOC. If the battery is discharged this way, this is 100% SOC. This is 0% SOC. This is the voltage which represents the state of charge of the battery. This is the 0%. This is not 0. This is some voltage. Maybe 3 volts. So if it is less than 0%, then the battery goes dead here. That means the operation has to be done in this range between these two voltage levels, the maximum voltage level and minimum voltage level. If it goes below this and superimposed by this self discharge, then the battery goes dead. The reversible chemical action cannot happen when the battery is discharged below a particular voltage. So this should be never done. So that is why charge equalization is to be made in this battery. That means when some of the batteries have reached 100%, sufficient time is to be given. That means the charging should continue till all the cells in the battery pack are equally charged to the same level. Means this is cell B, which is at lower level, then the time is given till this battery also reaches 100%. So that is this charge equalization concept. So that is why the most of the battery is charged quite instantly in many bigger battery packs. But for that means from 0 to 90% it goes quite instantly, and for 90 to 100% it takes some time. That is due to this charge equalization concept. Battery modeling. So all the batteries have some different dynamic behavior or dynamic response, which is governed by the mathematical model or the physical model of the battery. When that is to be represented by a mathematical model, that can be simply represented by this resistance in series with it. So this is the response from a battery. So if it is a simple resistance, when it is given a pulse, current pulse applied to it, then it has to behave this way in a step manner, but it is not behaving that way, but it is doing this way. Means there are more dynamics other than the resistance. Means some energy storage devices are to be used to represent this battery model. This is another battery model using the capacitor here, and another resistance has been used. So this way, electrical circuit can be used to represent the battery. So the purpose of this battery modeling is to predict the performance of EVs in terms of range, acceleration, speed, and all. So we will see why this resistance uh, kind of modeling is important. We will see this. So different battery SOH methods are there with SOC 100% and SOH 100%. The battery discharge represents like this. This is 100% SOC. This is 0% SOC. This is the voltage here. Voltage as a function of time. So this is time. So the battery is getting discharged. 100% SOC. With charging, it takes this kind of shape. With another kind of SOH like 80%, this lower point will not be here. Means lower voltage comes into picture much before this, maybe this point. So it will not be up to this point. This point. So this is for the case of SOH 80%. For the case of SOH 60%, trying this figure, it reaches the lower voltage quite before. So this is 60%. So means the battery SOH determines the voltage level as a function of time as the battery is discharged. So if it is fully healthy, SOH means state of health. If the battery is, I'm writing here, SOH is state of health. If the battery is fully healthy, means of 100% SOH, it means it can give higher ampere hours, means amperes multiplied by time is higher because for the same current rating, the time is higher here with the time difference between every SOH level. So it works for the battery works for higher time. So the ampere hour is higher. As the SOH reduces, as you have seen, the time of operation reduced. So SOH reduced means ampere hours reduced. So this is a brief description of SOH and the capacity in ampere hours. So the capacity significantly reduces with SOH reduction. So that is why the new batteries, brand new batteries of 100% SOH. So when the SOH reaches 80%, then the battery needs to be discontinued at this point when the SOH reduces to 80% because EVs, electrical vehicles, have stringent requirements on the performance parameters. So when the SOH goes below 80%, those requirements are not met by the same battery. So the battery needs to be changed at that point. So different SOH estimation methods are there. experimental methods, model-based estimation methods, direct measurement method, indirect analysis methods, adaptive algorithms, data-driven methods. Coming to these experimental methods, we will discuss all these. We will discuss all these methods. Coming to the experimental methods, so direct measurement methods, capacity or energy level test methods are there. Different capacity testers or energy testers are there, which can be used for knowing the FOH of the battery. Next one is ampere hour counting method. So what is the maximum possible capacity and what is the nominal capacity? That means this is the current or present. What is the present capacity and what is the nominal capacity? The ratio of these two things is the current SOH. So ampere hours, that means the current sensor is used and that measures the current over time. So current and the time gives ampere hours, amperes multiplied by time. So this is ampere hours. A simple description. So this can be counted, ampere hours can be counted, and from that what is the present ampere hours and what is the ampere hours designed. So this ratio gives the SOH. Another one is the third variant is the ohmic resistance measurement method. This is the open circuit voltage of the battery and a current pulse, discharge pulse has been given here. That means a constant discharge rate. Here 1C rate is mentioned, means for a 65 ampere hour battery, the discharge is 65 amperes. That is called 1C rate. Yeah, this is typical 1C rate for a unknown battery. So discharge is made at that C rate. Then this is the change in the open circuit voltage corresponding to that pulse. So in this, at the time of this pulse application, what is this change in the voltage? Is it delta V change in the voltage? This is the change in the current. The ratio of this change in the voltage divided by change in the current at that particular instant. At this particular instant, it gives this resistance. This is called internal resistance of the battery. Internal resistance of the battery, which is represented by a series resistor in series with a ideal battery. So this is the terminal voltage of the battery. As we have seen in the modeling phase, we have modeled this resistor. So that resistance comes from this analysis. So the next one is, so if this resistance is higher, SOH is lower. As the battery degrades, means SOH lower and resistance goes higher. If the resistance is double the initial resistance, means SOH has gone beyond 80%. That is a thumb rule. Electrochemical impedance spectroscopy method. In this, the voltage of varying frequency, various frequencies is given to the battery, and this impedance is measured. So the plot is the Nyquist plot is drawn between this real part and imaginary part, and different sections of this plot gives different components of this battery internal circuit. This represents this static electrolyte interface, solid electrolyte interface, constant phase element, the parallel combination of this given by this particular shape, charge transfer resistance and constant phase element that is modeled by this particular shape, and this shape is the Warburg element. So this is used for modeling the battery in a detailed manner. Direct measurement methods, cycle number counting. What is the number of cycles made by this battery in its lifetime? So if it goes beyond a particular number, such as 4,000 cycles, if this is the designed number, if the battery makes beyond this 400 cycles, it means that time to change the battery. Time to change means SOH has gone bad. So this kind of health estimation is used in the electronic devices like laptops. They use this kind of cycle number counting. When the cycle number exceeds a particular number, the laptop says that, prompts that it is time to change the battery. So destructive methods. For doing these methods, the battery needs to be completely disassembled to know the internal microstructures of the battery. Raman spectroscopy, X-ray diffraction, scanning electron microscope. So these methods are called post-mortem methods. Once these are done, the battery cannot be used again for the same job. So these are to be used when the battery is of no more use. Indirect analysis methods. So in this method, there are two ways of charging the battery. One is CC mode, means the current. This is current I. It is at a constant level. This is CC mode, and this is CV mode. Once the CC mode has been finished, means with this CC mode, the open circuit voltage becomes maximum at this voltage. When this maximum voltage, this is voltage as a function of time. This is a time as well. So when the voltage reaches maximum, then the control enters into this CV mode, means the voltage stays at this point and correspondingly the current reduces. So in this CV mode of charging, the behavior of the current is observed here in I, and different parameters are there to map this response as a function of this C loss. So based on these parameters A, B, C, and the current, so the C loss is identified. That is this charging curve method. ICA, incremental capacity analysis, and differential voltage analysis methods. So in this method, DQ, what is the rate of change of this capacity with respect to voltage? This is what is the change of this voltage with respect to the capacity. So these are different curves, and the relative peaks of these curves with respect to and positions of these curves with respect to each other gives the health status of the battery. That is another way of doing it. Indirect analysis method. In this indirect analysis method, ultrasonic waves are emitted and received, and in this process, the reflection, that means these are emitted towards this battery, and the reflections of these waves and the transformations of these waves are observed to see the deformations in the battery. And other health index methods are voltage change as a function of time. How is the open circuit voltage changing? That means when the charge process has been finished, then what is the change in the open circuit voltage? Is there any change in the open circuit voltage? Then the designed change. So that gives an indication regarding this SOH stack stress. So when this solid electrolyte interface in the battery uh, is increased, then the stack stress is observed. By observing this stack stress, we can know the health status of the battery and the internal pressure. So when the battery is degraded, then the gases form within the battery. So internal pressure also describes the SOH level. So these are indirect analysis methods. Coming to model-based estimation methods, there are different methods like um, equivalent circuit model based methods like extended Kalman filter, uncentered Kalman filter, particle filters, and all these different filters. Electrochemical model based methods means all the physics of the battery is analyzed, and based on that, it is said whether the battery is in good health or not. The combination of this ECM plus EM is here. This is combined methods. Data-driven methods, empirical model-based methods, data fitting, optimization algorithms, machine learning methods, sample entropy. So all these are different model-based estimation methods. So this is a typical diagram of these model-based estimation methods. Current temperature, battery cell pack, and then this data is collected here. The measured voltage is here, and there is an estimated voltage from this battery model, and this produces this error, and that is given to this Kalman filter, particle filter, different filters. Then this capacity or this self-discharge, all these are estimated from these filters, which which show the SOH. So coming to these methods comparison, so there are different merits and demerits for all these methods. So direct measurement methods, indirect analysis methods, adaptive filtering methods, data-driven methods. The most direct and simplest methods are here. Easy combination with the model-based method, accurate in laboratory environment. EAS and destructive methods can be used to study aging mechanism. Coming to indirect analysis methods, get aging information from the measured external characteristics. I see a DV and ultrasonic can be used to study aging mechanisms in real time. Accurate in laboratory environment. Adaptive filtering methods, accurate and good robustness, easily applied for online battery energy storage with different chemistries. Less pretest is required for the case of data-driven methods. Precise estimation of slowly changing parameters such as battery life and health. So this way, different disadvantages are also there. Improving directions for online and ECAS realization combined with suitable battery model, develop offline maintenance and diagnosis strategies, methods to obtain online IC and DVA curves with less computation complexity. It is an improving direction here. Applied combining with machine learning methods, considering the impact of temperature, all these are different improving directions for the indirect analysis methods. Improve ECM with more physical meanings, improve electrochemical models with more aging mechanisms, develop a multimodal fusion method to improve applicability, combining machine learning and big data methods on board, adaptive filtering algorithms to improve the accuracy and robustness of on-board algorithms in real-time applications. All these are improving directions for the data-driven methods. So as previously discussed, this one, what is the remaining capacity and what is the nominal capacity? The ratio of these two is the percentage SOH. So I will now discuss this ohmic resistance method in the direct measurement methods. So we use this ohmic resistance method for the SOH estimation and status classification of the battery modules as a part of our project in University of Huddersfield, UK. So I will now discuss our experiences in this project. So we used a pulse test technique. So this is a pulse is used here, which starts from 0. This is not perfect step. Pulse, perfect pulse. So at this leading edge, this is called leading edge and this is called trailing edge. So at this leading edge, as explained before, or at this trailing edge, we see this change in the voltage and change in the current. So that gives the internal resistance of the battery. So this is the quickest way to know the health state of the batteries. So this takes only a single pulse and gives this internal resistance. We don't need to use time-consuming ampere-hour counting, amperes multiplied by time. This method, ampere-hour counting, this is quite accurate, but takes a lot of time. Time is more here, but accurate here. So in order to remove this situation and to be able to uh, comment on the health state of the battery, simply we used this internal resistance using pulse test technique, PTT here, or ohmic resistance method, as described before. And for this, we used many battery variants. And for making this test done, we used different equipments or components like a computer, NI DAC card, NI breakout board, chroma devices. That means it is a programmable DC power supply, multiple in number supplies, master chroma, slave power supplies, programmable DC electronic load that is also used here. Interface NI lab view in order to control the test and measurement systems from a computer. We used NI lab view. Differential voltage measurement probe means voltage sensor. Current clamp means current sensor. So another current clamp, digital multimeter, other equipment, laboratory DC power supply, oscilloscope, resistive loads for system testing, HV tools, connecting wires, insulating tapes, batteries, Hankook, lead acid batteries, Electra lithium ion batteries, Nissan lithium ion batteries, first generation, second generation of the same variant, Citroen DS3 lithium ion battery. So all these batteries have been used and some more batteries are coming into the laboratory for testing. And the equipment components used in the continued version of the same. So Newware battery tester. This is a battery tester for quickly testing different modules. Safety and protection equipment, fire blanket. In case of fire comes into action picture, then we need to use this fire blankets. Fire blankets small in size, CO2 and H2O cylinders. All these are equipment or components used for our project. So this is a control scheme, computer control of charging, discharging, and PTT. Computer with NI lab view is used here. NI PCI 6299 DAC card is used, and its IO board is used. Signals to analog interface through this DAC card. Signals are given from the computer to the DC power supply as analog signals, and the voltage and current signals are also given into the computer uh, through this DAC card again. These are the current sensors. This is the current sensor, and this is the voltage sensor. A DC power supply is there to charge the battery. This is the UV battery here. To charge the battery, DC power supply is used, and to discharge the same battery, a DC electronic load is used. This is controlled by an USB cable, and NI lab view. The computer with NI lab view controls all this process. These are a few pictures. This is the power supply, and this is the analog interface, and these pins have different specified functions. We need to program. That means we need to use some analog signals to it to make the equipment behave in a specified manner. NIPCA 6299 IO board. This is the IO board for the DAC card. DC power supply. DC electronic load. So all these are different interfacing ports. So this is a voltage measurement probe or voltage transducer, current transducer. This is discharging and charging setup. This is charging and this is discharging. And the system is tested on a lead acid battery like this. This computer has NI lab view here. So the same setup here. And newer battery tester. This is the battery tester we used. It has 8 channels, so which can simultaneously test 8 modules at a time. And these are the batteries. This is a lead acid battery, and this is a full lithium-ion battery pack from the vehicle Nissan Leaf, which is a celebrated variant in Europe, EV variant in Europe. And these are different lithium-ion batteries from a truck, uh, lithium-ion batteries from a truck. And this is the view of this Nissan Leaf, the same Nissan Leaf pack. There are different sections, 1 to 5. Totally, this has 48 modules. This is a simple sample lab view code. Control the charging and discharging processes. So this is the battery module, and there are 4 cells. The cells are connected in 2P2S configuration. Means there are 2 parallel paths in this module, and in each parallel path there are 2 cells connected in series. So totally this pack has 4 cells. This module has 4 cells. The voltage range is ranging from 4.2 volts to 3.3 volts. Voltage ranges between these 2 levels. This is that particular cell, which is quite fragile. That is why we need some mechanical strength. That is why this metal structure is used here. This has a positive terminal as well as negative terminal. The middle point here is the cells joining. So The internal resistance is computed, as I said. The transducer signals are there, and different sampling frequencies are tried, and the different pulses in a row are applied to the battery to know the different RIs. All these RIs are average to get average internal resistance, which shows the health condition of the battery. To different at a different SOCs, all these internal resistances are computed, and different C rates, different C rate pulses. The internal resistances are computed in these are in milliohm. The typical values are between 2.25 and 1. Yeah, these are the typical values. And we observed as a part of our project, we observed that this resistance is a function of time. So when the battery charged or discharged as a function of time, heat is developed in the battery. This heat development uh, reduces the internal resistance that is determined. That means R is determined, reduces with temperature increased. If the temperature reduced, internal resistance increased. That is the relation we found. So when the temperature is increasing like this, then the resistance is coming down like this. So in order to obtain an accurate value of this internal resistance, we need to have a thermal chamber or a temperature chamber. Some people use climate chamber as well, which has control on the humidity as well. So this is different cooling arrangements we used in order to reduce the in order to make the temperature constant. So all these are different average resistances for different modules. To the laboratory hardware and systems. So this is the power supplies are connected in parallel combination to reduce the to increase the current rating. Each power supply is capable of giving 25 amperes, 25 amperes to increase the current discharge current to increase the charging current to some higher value so that the charging finishes quickly. All these are connected in parallel operation. So they could give 75 amperes in this connection, and the battery test voltage is 450 volts. So lab shelving and packs being disassembled to module level. Battery fire blanket storage or dispenser. This is the battery fire blanket right from here to here. In case of any fire develops, this blanket needs to be deployed onto the battery. This is the battery. It has to be covered. It has to cover this battery so that the fire is extinguished. That is the concept. Laboratory hardware and systems. Power supply to Nissan Leaf. Some fuse is used here. So if while testing the battery, the BMS, there is battery monitoring system, that BMS is removed so that to have control over the battery modules. When this BMS is removed, there is if this positive as well as negative, these terminals are connected together. then there will be a short circuit, which is not at all desirable. So if this kind of short circuit it happens outside this uh, fuses, suppose say here this this is connected to this port, and if this kind of short circuit happens here, then these fuses protect this battery being damaged, and the eventual fire is also avoided, will also be avoided with this kind of fuse arrangement. So that is the purpose of this power supply to the battery, fused power supply. So the battery temperature is held constant almost with the different cooling arrangements. With this, we could see a bathtub curve kind of behavior in the internal resistance as a function of SOC. So it should be higher at both ends and should be lower in the in between values of SOC. So that was observed. So this is different temperature analysis results. These are different temperature analysis results. Means when the temperature is reduced by 17.05 percentage, the resistance is increased by 6.52%. So this is the relation we found, and with the increment of this temperature by 10.59 percentage, the resistance is reduced by 10.20%. So this is the relation we observed from our test, and this is a typical resistance versus temperature behavior. We fitted a curve here, and this is the fitted curve relation, mathematical relation. So from this, when a reference resistance and the reference temperature are known, based on the current temperature, we can estimate the resistance of the battery. That is what is this analysis. So after that, full pack testing has been done. Earlier module level testing was done, and after this full pack testing was done. So these are the components used. DC electronic load, its power supplies in parallel configuration. So CC mode of charging, PV mode of charging, as I said earlier. Different pulse test and different resistance obtained at both edges, leading and trailing. Then after that, this is the capacity testing. This is the full voltage, and this is the that means this is the voltage correspond to 100% rate of charge. This corresponds to 0% rate of charge. So on this battery, it was labeled as the SOH is 63.46. So as per that, the ampere hours expected are 41.88 ampere hours. Watt hours expected are 15.23 kilowatt hours. So from this test, we could find the figures close to this 41.324 ampere hours here, 15.32 kilowatt hours here, which is close to this one, and this one is close to this one. So different. So this is danger signboard. So as the batteries are dangerous in nature, as they can explode. So this kind of danger signboards have been used in the laboratory. So Nissan pack, the same pack, pulse test at different sources is done. So this is the internal resistance versus the SOC characteristic. So at 0%, this is the SO, that means internal resistance in milliohms. 40% SOC, 2.85 milliohms, 100%, 3.145 milliohms. So this is like this. That means higher at both ends and the lower between values representing a bathtub curve. More points are to be explored. So this is our testing in UOH. So the purpose of this testing is that after testing these batteries in terms of the internal resistances, these battery modules can be used to um, once these are obtained, they can be arranged in energy storage systems. That is the purpose of this classification, battery sorting and classification. So initially, as I said before, the SOH is 100%. So when it goes below 80% SOH, then that is to be discontinued ideally. But if the SOH figure is known at around 70% or 60%, that those are discarded by the user, as the EV will not deliver as per the design, as the EVs have stringent requirements on the performance. So this kind of SOH figure is not enough for meeting those requirements, such as speed, capacity, range. So these are not met by the batteries, so those are to be discarded. Then at this stage, they become retired batteries, retired EV batteries. So we get these retired EV batteries, and we can sort the batteries at either module level. That means we need to disassemble the battery pack into different modules, and after that, our another choice is that pack level. Pack level means we can know the health condition of the uh, modules SOH. So if the module health condition is known, for smaller energy systems, these modules can be given. So if the energy system is bigger, then we can just know the SOH, and we can just mm, arrange different various packs of the same SOH level in another energy storage system of high rating. If it is high pack level, um, sorting is done. High for high energy storage system, bigger energy storage system, pack level sorting is done. For smaller energy storage systems, module level sorting is done. So that is the purpose of our project. So coming to the generalized discussion of this reuse of retired EV batteries, the cathode materials, electrolytes, and solvents of lithium-ion batteries cause certain level of pollution and harm to land and water. That is why we cannot just simply throw them into the environment. We can either recycle them or reuse them. Recycle means extracting all the materials, which will be discussed now. The cobalt in lithium-ion batteries is very active element. If retired lithium-ion batteries are disposed of improperly, safety problems such as combustion and explosion may occur. So retired lithium-ion batteries are urban mines. On the other hand, they contain various rare and precious metals such as lithium, nickel, and cobalt. So those are to be either recycled or reused. We will discuss that now. So all this material has been obtained from this reference, sorting and regrouping and echelon utilization of the large-scale retired lithium batteries, a critical review that is in Renewable and Sustainable Energy Reviews, Volume 146, published in 2021. Echelon utilization means reuse of retired EV batteries. So some sorting as done in our project in UOH is to be done for the reuse of the batteries. We will discuss these concepts now. So reuse of retired EV batteries. So these are different months: January, February, March, April to June, and we see that these are global EV sales. Those are increasing in number. Coming to the first half, that means uh, the first of 2019, first of 2018, there is an increment in the figures, EV battery sales figures in China, Europe, USA, and other countries as well. So the use of electrical vehicles is increasing. So in the same proportion, retired electrical vehicle batteries also come out. So mm, those are to be properly used. For manufacturing the batteries, first we get the raw material and the manufacturing is done. And after that, once the batteries are manufactured, those are used in EVs. And once those are retired, means SOH is less than 80%, those are recycled directly. Means valuable materials are extracted and the residual waste is disposed of. So this is a recycling, direct recycling. So another way is Echelon utilization, means reuse of retired batteries. Means when the batteries are retired, sorting and reorganization is done as done in your project in UOH. So these can be used in various applications like for second use, Echelon utilization, use of retired batteries based on the sorting and reorganization. So after this echelon utilization also, if the SOH falls below 40%, then those are to be recycled. That is this echelon utilization concept. So many other requirements other than this electrical vehicles are of not such stringent requirements on performance criteria. So these retired batteries can be safely used in other applications. So we will discuss those other applications. So whatever it may be, cell level alkaline utilization is not recommended from the perspective of economy and safety, because if we go for alkaline utilization, still cell level means there are two levels: stack level, module level, and cell level. Stack level is for bigger energy storage systems. Module is for smaller energy storage systems. Cell level is for much smaller, but this is not recommended because of high labor to be used for this, and moreover that it is not safe for the environment because of residual waste, not economical as well. So safety is the important factor in effluent utilization. Differences in battery inconsistencies, operating environment, operating conditions, driving habits of the driver decides different battery consistencies. So some batteries are of the same voltage, open circuit voltage level because of good driving habits. When, so all these conditions are to be kept in mind before sorting different batteries of consistent parameters. So echelon utilization, same vehicle model. The sorting and grouping is recommended when the battery modules come out from the same vehicle model. Mixing and regrouping of batteries from different environments should be avoided as much as possible. Low C rate operation with proper BMS, that is of highest importance because safety is the important factor for this echelon utilization. We cannot go for high C rate operation. High charging as well as high C rate discharge is not recommended at all. So low C rate operation with proper BMS is recommended for echelon utilization of the retired EV battery. So as I said, there are some applications which don't have that much of stringent requirement on performance criteria. Such applications are personal housing, telecommunication towers, low-speed electrical vehicles, energy storage stations, renewable energy systems. So these can be safely used here. So in case of user side electrical storage systems or stations, then the users can use this ESS for energy storage in case of power failure. Grid side ESS, this is for controlling the peak load demand. Power side ESS for controlling the power fluctuations. So in renewable energy system, wind storage, renewable energy system, wind PV storage RES, PV storage charging RES, different applications are there. So coming to this low speed electrical vehicles, so they don't need to speed up. That means acceleration, this kind of high speed, all these are of low requirement in that case. These vehicles are um, cycles, bicycles, mobility vehicles for elderly people, that kind of low speed electrical vehicles can use the retired batteries from the used, that means used battery packs from the electrical vehicle or retired battery packs. So sorting and grouping and reorganization is done, and those batteries are given to this station. So reuse of retired EV batteries in a typical PV storage charging microgrid system. So this is straightforward. PV array, wind turbine, grid, retired lithium-ion pack, supercapacitor, all these are different sources, and those are used here in a microgrid system. So in reuse of this retired EV batteries, both the cost and the economical value are important. The cost is decided by battery cost based on these various factors: battery capacity, battery power, energy density, fault, purchase cost, transport cost, storage cost, dismantling cost, sorting cost, degrouping cost, construction cost, economic utilization scenario, different operating costs. So the benefits of, given are differences between peak, yeah, all in the power grids, government subsidies, income from delaying grid upgrading. So if these are used as energy storage system, then we don't need to upgrade the grid to meet the peak demand from the grid. So this is another benefit. Environmental income means if we protect the environment from the hazardous substances, there is a revenue from there as well. Residual value of battery material recovery. So all these are different economical values. So a compromise needs to be made between these costs and benefits. So these are different scenarios in which the batteries fail. This is a uh, negative electrode, and this is a positive electrode. And here coming to this collector is copper current collector, and this is aluminum current collector. So copper dissolution and dendrite formation, solvent percolation and graphite exfoliation, and SCA decomposition and precipitation, particle cranking, SCA formation and buildup, lithium plating, and dendrite formation, So all these are different modes in which the battery's capacity reduces. Because of all these effects, the capacity reduces. These are called side reactions. So once um, this particle cracking, SCA formation and buildup, so this kind of all these happen, then this positive touches the negative one, then there will be an internal short circuit to the separator here. The separator is there here, but these dendrites penetrate into the separator to touch the opposite polarity electrode, then a short circuit, internal short circuit happens. So then, as you know, fire can happen and damage can happen to this battery and not good. So reuse of these retired EV batteries are to be used with caution, of course, considering all these into mind. So those can be sorted based on this molecular scale sorting, micro nano scale sorting, micro scale internal structure sorting, macro scale outer characteristic sorting, lithium precipitation, SCA film thickening, anode material falling off, other reactions, all these are considered here. Flatulence, leakage, outward appearance, electrical characteristics, and others, all these are observed here to decide on the macro scale sorting. So the accuracy is high here, but the time consumed and the material going waste is also high. And complexity is also high. Coming to here, accuracy is low, but the complexity is low here. But sorting can be done. So, reuse of retired EV batteries. So when a battery comes out of a vehicle, when no historical data is available, so all these batteries can be equalized. Their charge can be equalized. Short time series charging. So this is different charging characteristics and the feature information is extracted, internal resistance model. So the internal resistance is computed and the correlation model of charging characteristics and capacity that is obtained that gives capacity. So based on these figures, then sorting can be done. So all the batteries of same internal resistances are grouped together. All the batteries of same capacity are sorted together and so on. There are different criterion. So once those are sorted, those can be given to various applications like energy storage systems, so which can interface with the grid. There are many other applications like low speed electrical vehicles and so on. So all the batteries of same characteristic are to be sorted together. That is the criterion for this. Reuse of retired EV batteries. In this, no historical data available again in this case as well. That means uh, rapid life prediction of lithium-ion batteries without historical data. So a data-driven method is used here, and a model prediction based method is used here, and EA, that means estimated capacity from this data-driven model, and this is the estimated capacity from this model prediction. Then all these are combined to get this combined capacity. Then based on this can be sorted. That is another way of doing it. Then when historical data is available, so when the batteries EVs are getting charged in charging stations, that charging data can be stored into the cloud. So that cloud can process that data to sort the batteries in order based on different parameters. So with this way, no specific equipment is required for sorting the data. So as the EVs are getting charged, the data goes to cloud. The cloud itself analyzes the data and sorts the batteries, and it gives the information for sorting. That is another way of research nowadays. So this is the capacity in ampere hours. time per day, mean prediction point, prediction interval, and this is the capacity. Capacity is being decreased from this prediction characteristics as a function of time or delay, and the resistance is increasing as a function of time or day and the usage. So this kind of analysis can be made based on the historical data available. So another one is multi-level and multi-dimensional classification method based on echelon utilization scenario constraints. So first of all, we need to see is the side reaction, because side reaction decide the safety of the lithium-ion batteries. First importance is to be given for safety. So all the batteries are of same side reactions are to be sorted together, like similar solid electrolyte interface, similar dendrite formation, that kind of similar capacity degradation, that kind of all these are considered once that classification is done. Those remaining batteries in a particular classification can be sorted again, which is called a second level classification. In this multi-dimensional classification, algorithms can be used based on energy scenarios. In the case of high energy scenarios, we need to have high capacity batteries. That means ampere hours and watt hours of the battery are required to be higher in this case. So in this way, capacity versus life, this kind of sorting is done. So all the batteries of same capacity as the same group are to be sorted together. So all these modules are sorted together. All these are sorted together. All these are together. All these are together. That is this one. In power scenarios, if the application requires higher power, then it is required that internal resistance is lower, because uh, terminal voltage is given by open circuit voltage minus internal resistance into the current, load current. So if the internal resistance is higher, then this drop becomes higher, then the terminal voltage drops. So power is given by Vt multiplied by I. So this power reduces. For that, internal resistance should be lower. So this is the classification based on the internal resistance. So multi-dimensional classification one can be done here. So this is group 1. This can be sorted together. Group 2, group 3, group 4, this way. So energy power scenarios, all these are considered together, and all these three-dimensional space is used for sorting the batteries. Yeah, this is the session today. This is the end of the session. Thank you very much, and I welcome any questions now.
Good afternoon, sir.
Yeah, good
Dear
afternoon.
participants, today Dr. Vidyasagar sir enlighten us related to the problems with electric vehicles, types of electric vehicles, and particularly what are the hybrid vehicles, what type of fuels we can use it. And he has given presentation on journey distance analysis and battery performance criteria and comparison between various commercial batteries and lab hardware and systems and reuse of retired batteries, recycling aspects, and many concepts he explained nicely. And non-technical candidates also can able to understand the type of presentation sir has given. Very few persons are available across the globe who have good awareness about this design and development of electric vehicles. One among them is Dr. Vidyasagar sir. Thank you very much, sir. And some of the participants, they kept the questions in the chat box. And
Mm-hmm.
one is from Professor Kulkarni, and his question is how discharging of batteries deal with modeling for various types of battery. How
So
discharging
discharging
of
of,
batteries deal while modeling of various type of battery.
yeah, so modeling of various types of batteries. So the internal resistance plays a major role here. So if the internal resistance is higher, then the battery capacity drains out quite quickly because the voltage drops quite quickly to the lower voltage limit because of this internal resistance and different other resistances uh, as determined in electrochemical impedance spectroscopy. Because of this voltage degradation, the battery reduces, that means the voltage reduces to the lower voltage limit quite quickly compared to the new one. Then this decides how at what rate the battery can be discharged. And it can be observed that with high rate of discharge, the capacity that can be obtained from the battery is lower compared to lower current discharge of the same battery from the same SOC level. So the discharge current also plays an important role here, and the internal resistance plays an important role here, and the temperature also plays an important role here. If the temperature is low, the discharge is governed by that. So we need to consider the relation between the capacity and the temperature, internal resistance and the temperature, and the different aspects. Yeah.
Thank you, sir. Next query is from Mr. Murugan. Sir is putting the query. SOH is available with commercially available vehicle or not?
Means his question, I think, I am thinking that his question is regarding the BMS. BMS also shows the SOH, but for most of the manufacturers, the BMS is made in such a manner that SOH information is not available online. If they make the SOH information of the battery online, that means available online, if that is made available online, then the user knows the health condition of the battery and he wants to go for replacement when he notices that the SOH has gone bad. So in order to reduce the request from the user to replace the battery, they make this information hidden, most of the BMS manufacturers. So that can be obtained through special tools only through some CAN output tracking. So yeah, that is available, but that is not generally given to the general user. That is the current scenario.
Thank you, sir. You have given a demo about the uh, lab hardware and systems.
Yeah.
Mr. Dinesh Kumar Sharma is asking the question, and Mr. Rahul Sen also asking question. How much investment is expected for this type of lab setup, sir? And what is the overall costing of the lab? Whether it is funded lab or institute is managing?
Yeah, it is a funded project. We are working on Innovate UK project. So that is funded by that UK. So coming to the cost, these equipments are quite costly, at least in UK. Means the battery tester typically costs around 50 lakhs based on the number of channels and based on the manufacturer. There are some more manufacturers from China battery testers. So those are available at around 20 lakhs. Yeah. So reliability, all these are also to be considered. Yeah.
Sir, next one is from Mr. Murugan.
Mm,
He is putting the query, what is the current research?
mm.
That is, what is the ongoing research related to SOH?
SOH, yeah. So this sorting and regrouping is the ongoing research. Many institutions are doing this nowadays. Apart from this, the making the retired EV batteries into this energy storage systems and giving support to the renewable energy systems is another research area. And recently formulated, that means noted some research areas I will read out for him. So the graphene batteries for electrical vehicles, sorting and grouping of EV batteries, as I said, grid independent charging facilities for EVs, retired EV batteries as a support to the grid. So all these are different ongoing research topics.
Thank you, sir. Next one is from Dr. Hemaraj. His query is, what is the lifetime of reusable retired EV batteries? For retired EV batteries, we discussed the methods. He is asking, what about the expected lifetime?
Yeah. So the original lifetime of the battery from 100% SOH to 80% SOH is 4 to 5 years. So beyond that, if those batteries are used in retired applications, the SOH is ranges from 80% to 40%. So the range here is 40% instead of 20%. So the expected life is 6 to 8 years. You can use the same battery for 6 to 8 years for low power requirement applications.
Okay, thank you, sir. One more, the last query. In India, Vespa electric scooter is launched. They are quoting that they are using 4.2 kilowatt hour lithium-ion battery,
Okay.
and it will run for 100 kilometers at a time.
Mm-hmm.
If you can replace this battery with other material, the cost can be reduced, because now they are quoting the price as 90,000 to 1 lakh. Depends upon the tax, something variations will come. 90,000 to 1 lakh they are quoting. Our participants are asking, is there any work is going on to replace this lithium-ion battery with any other material?
Okay. With any other material means lithium ion batteries are, as I explained in this session, are of high specific energy. So because of that, weight is reduced. If we use any other batteries for the sake of this cost, then weight can increase. So some other batteries are in research, like graphene batteries. So that is ongoing battery technology. So that is more costlier because the research is going on. So the current solution for this to bring the cost down is that to sort and group the same retired batteries and the batteries, if the second hand batteries or second life batteries are used for the same application, then the battery cost reduces significantly, because the second life battery also can meet the same demands of the road usage. And the cost is it is cheaper by at least 50%. So if the original battery costs some 40,000 rupees, then this can cost only 20,000 rupees. So there can be a saving of 20,000 rupees in this.
Thank you, sir. One question from our organizing committee side. Recently, many cars have been launched, which can run up to 500 kilometers at a time. One is RD GT car up to 500 kilometers, 93 kHbW battery. It will be charged in 22 minutes up to 80%, and 40 minutes up to 100%. BMW, it has a 76.6 kHW battery, and it is taking 7 hours.
Okay.
Like that, they are quoting different charging times, and duration also varying.
Hmm.
Is there any work is going on to complete the charging in short time?
Okay, that completely depends on the battery
Yeah.
chemistry.
Hmm.
Some battery chemistries support that kind of fast charging, and for the same chemistry, for different SOC levels, as you said, the charging time is higher. That is because of the chemistry not being supportive. So, if the chemistry is made in such a manner that the charging more faster charging is possible, then that is definitely possible. So research is anyway going on every single day to reduce the charging time, yeah, and other aspects, other problems with the EVs. So definitely in future, we may see batteries with very less charging time.
Okay, thank you, Dr. Vidyasagar sir, for sparing your valuable time to enlighten us on the aspects of EV battery SOH estimation. Uh, I'm conveying thanks once again from the organizing committee side.
Okay.
Irrespective of the adjustment of the time, even the time is not convenient here at UK, still you considered our difficulty and you spared the valuable time to wake up too early in the morning to enlighten us. Thank you very much, sir. And
It's
very
not a
nice
problem.
section. Participants also very happy
Yeah, yeah,
to hear your lecture and hope you will have fruitful interactions in future also. Thank you very much,
yeah.
sir.
Yeah, thank you very much. So I am also quite happy to be a part of this FDP, which has many hundreds of participants or even thousands of participants being registered. So I am happy to be here as a part of this FDP. Thank you very much, Dr. K. Sridhar.
Sir.
Yeah, thank you
Sir,
very much.
thank you, sir. Thank you, sir. Dear participants, with this one, we are closing today's section. Tomorrow, this section will start at 2 p.m. because speaker is from Italy. For time adjustment, we are planning the session as 2 p.m. Join by 2 p.m. to tomorrow. Thank you very much, sir. Vidyasagar, sir. With this one, we are closing the section.
Okay, thank you very much.